Yeah, today is Lewis structures for labs, so I'm going to talk about Lewis structures, but starting from the very beginning.
I have a question regarding the ionization.
All right.
So for the ionization energy, it's always the metal, right? And for the electron affinity, it should always be the non-metal, right?
No,
It doesn't matter.
it doesn't matter. Ionization energy is for any element. Metals just have low ionization energy, but nonmetals have much higher ionization energy. You can still take an electron off a nonmetal like fluorine. Fluorine has a very high ionization energy. It's difficult to take an electron off of it because fluorine's small, for one, but it's not the highest. Do you know what the highest ionization energy is?
Chlorine.
Not chlorine.
Helium.
Helium. Helium has the highest ionization energy. And so ionization energy is for everything. Electron affinities for everything as well. All ionization energies are endothermic. You know, they're all going to cost you. However, electron affinities, most are exothermic, and that includes metals. Metals, you don't expect them to gain an electron. You expect them to lose an electron. And so it's a little unusual. All right, for chapter 10 and 11, I'm going to change the lab, experiment 8 and 9. We're going to combine 10 and 11 so that when we analyze these structures, we can extract the maximum amount of information from them that we can. And the thing is, chapter 10 and 11 deal with compounds. And so let's talk about the types of, actually, before we talk about that, compounds, we're just looking at structure. And bonding. And so what types of bonds do you guys know already? You know about, like, say, metallic bonds?
Hydrogen bonds.
Okay, hydrogen bonds and London dispersion are different. Hydrogen bonds and London dispersions are what we call intermolecular forces, not actual bonds. Bonds are going to be quite a bit stronger. Like, say, a hydrogen bond is only about 25 kilojoules per mole, and that's easy to break. It's not that significant. Whereas the weakest covalent bond, which would be like an iodine-iodine bond, iodine-iodine bonds are easy to break. Why?
They don't overlap.
It's so big. These are gigantic atoms compared to fluorine. Fluorine, both of these occur as diatomic molecules, but you know, iodine's a lot easier to break apart. These are big, small. Iodine bonds are about 100 kilojoules per mole. So, well, anyway, going to metallic bonds, these would be like the bonds in sodium or magnesium. Let's look at magnesium metal. If I look at the bonding in magnesium metal, see Mg solid, what do I see? Now, there are different ways we visualize metallic bonds. One way is we use the electron C model. The other is we use band theory. Both of these are in chapter 12. But let me just briefly talk about the electron C model. In the electron C model, the nuclei are fixed in position, but the electrons are not. The electrons are pretty much free to move anywhere, at least the valence. And so the electrons are thought of as an ocean surrounding these fixed pylons. And so this is why it's called the electron C model. And so if you have an electron here, it's pretty mobile. And this electron C model also gives rise to why an electron in a metal, a solid metal, has a continuous spectrum. Why would you think an electron in a solid metal would have a continuous spectrum? Because it's essentially free. It's a free electron. It's not constrained to one atom. And so when we're looking at the wavelengths, it's easy to add another half wavelength in there. And so this is why I want to talk about the electron C just briefly now, but we're going to come back to band theory in chapter 12. And we aren't really going to talk about metallic bonds in 10 and 11, but I wanted to bring those up now. Then we have ionic bonds, right? Ionic bonds. And so let's take a look at an example of ionic bond, like sodium chloride. If we look at sodium, sodium has one valence electron. And you guys are familiar with Lewis symbols? Mm-hmm. And then what's the Lewis symbol for chlorine? It's a Cl with how many dots? 7. And then what's chlorine going to do? Chlorine is a good oxidizer, and in fact it has the highest electron affinity, which means it really wants an electron. And does it cost much to pull an electron off sodium? No. At 500 kilojoules per mole. It pulls an electron off sodium, and we end up with this. We end up with sodium chloride. Now the Lewis structure for sodium chloride is we use these square brackets when we have charged ions. It's going to look like this. This would be the Lewis structure. Now how do you show the bond between a sodium ion and a chloride ion? How do you show the bond? In other words, should I draw a line between these? No. In fact, this is the bond. The bond is that I have a positive sodium sphere. Actually, let's take a look at sodium and chlorine because this is an easy one to do. If I look at sodium versus chlorine, they're in the same row. In other words, they're in the same shell. In other words, they're in the same period. And which is bigger, sodium or chlorine? Sodium. About how much bigger? About 2 times bigger. And so this is how they start off. Chlorine is smaller. Why is chlorine smaller? It has a bigger Z effective. This is going to pull in the electrons closer. However, what happens when we form the ion? When sodium loses an electron, it forms sodium plus, and what happens to the size of that? It shrinks by about half. And then chlorine, when it gains electron, its size just about doubles. And so it flips the size. And so this is now positive, this is negative. What an ionic bond is the attraction between a positive ball and a negative ball. They're going to come together and touch, and that's going to be the bond. And to break this bond, you have to pull apart the ions. It's going to cost you energy. And so that's an ionic bond. But we know that sodium chloride doesn't form just one ionic bond, right? We're going to form a lattice. Now the lattice for sodium chloride is going to look like this. We're going to have, actually let's do different colors for the lattice. We're going to have sodium, and it's positive, so it wants as many negatives around it as possible. And so I can fit how many chlorides? 1, 2, 3, 4, 5, and then 6 underneath. And so actually, as far as each sodium goes, it's ionically bonded to 6 chlorides as nearest neighbors. But we know it doesn't stop there because the lattice extends out in 3 dimensions. And so this just continues on and on and on. So we just go, etc. And so the first point that comes up is this. Delta H for the bond, one bond is not equal to delta H of the lattice. In fact, the lattice is much stronger because there are lots of bonds. And so if you have 1 mole of sodium chloride, how many bonds are you breaking in order to completely break it apart? No, much more than 6, because you have 6 nearest neighbors, then you have however many next nearest neighbors, and then the next, and so on. And so you have to look at that over 3 dimensions. Obviously, it's going to weaken the farther you go out, but there's still an attraction there that has to be broken. And so there's not just one bond. The other funny thing is this called a molecule of sodium chloride? No, what do we call this? We don't call it a molecule, we call it a formula unit. This is a formula unit. Because a molecule has to be a discrete unit. But when I look up here, do you see an individual molecule of sodium chloride? No, you pick any sodium, and which of these 4 or which of these 6 chlorides belongs to it? All of them. Right? And so there's no such thing as a discrete unit here in an ionic lattice. Therefore, the smallest unit is called a formula unit. Here. But anyway, this is quite favorable because it's going to cost you about 500 kilojoules per mole. You're going to get a little bit of energy back, right? What is electron affinity? This is 500 kilojoules per mole. Chlorine has the highest electron affinity. The highest electron affinity turns out to be only negative 390 kilojoules or so. So that is about 400. And so it costs you 500, you get 400 back. This is going to end up net costing you about 100. So this costs you about 100 to make the ions, but you're going to get that energy back by forming the lattice. And here's the payoff. Here. And this is the lattice. This is extended 3-dimensional network. Okay, so that's the structure for sodium chloride, which has an ionic bond. Let's look at something else that has an ionic bond, and this would be sodium carbonate. Now, carbonate is going to look a little different. Let me just show you what carbonate looks like. Carbonate looks like this, where the net charge is 2-. Carbonate has something called formal charges on each of the oxygens. These are negative and negative. And so the net charge is the sum of these 2 negative charges here on the oxygen, which makes it a -2 ion. These formal charges don't always have to be shown. We're not going to show it here right now. We'll talk about it later. But I drew it already, part of it for you. Can you complete the Lewis structure for sodium carbonate for me? What is the Lewis structure for sodium carbonate? So go ahead and try to finish that.
Because in reality it's going to go on either side.
You should come to HTC with me.
I will. I'll go to HTTP.
Oh, no, HTC.
They're closed,
I'm
actually.
so
No, they're not.
tired
They're
right
open till
now.
5.
Are you gonna make it till 5?
Yeah, we can finish here early.
Oh, today, huh?
Stop cock blocking him.
What are you talking about?
It's mean to him.
Why? Is she hot?
Here.
Yeah.
No, she's like 50.
No, she's not.
Yes,
She
she
looks
is.
like she's 30 though.
No.
Hair.
She graduated, she got her master's in 1996.
You're lying.
I'm not. I looked her up.
I remember that you.
God.
No, because she came from Hawaii too. So.
That is your best friend.
Here. No. You asked me about carbonate. This is carbonate.
You can put the 2 and 8 on the
Jeez.
side. This is how it didn't look.
You're wrong.
It's 2 and 8.
No, I don't think that's it. I'm sorry.
Why
I don't
would-
think it's it.
Why should you do it?
Here.
He wants us to rob the sodium. Oh, that's how he wants it? He wants us to-
Yeah, but he already dropped the force. We have to put the sodium somewhere. That's what he's saying. And the root structure. It has to be like
I put it on both sides.
Oh, isn't this that too? I told you there's something outside. Wait, it has
You can do it. So they should balance each other.
Let's do something.
Is it like this?
I feel like this room is
Could be. There's a problem with yours, though. Maybe you can figure it out.
Like mine are too.
No, mine. I should
Oh,
this is yours.
yeah, wait, why can I do it?
Maybe it's just like any two.
Also show there's a problem with yours.
I know, it's too.
Try to figure it out.
So color. Yeah, it's good, you're right. That's
Doesn't
how I
show
did.
them
I
yours.
said,
Okay, who's showing yours then?
no, because we did this wrong.
Talk about
That one?
insecurity.
That's it.
Dr. Shabala said,
What you said?
what is it?
It was wrong for sure.
That's not what I'm saying.
Oh.
Isn't that what you said?
No, he said that.
No, I.
Can you come look
I
at this
told
one?
him you were like.
All right, let's talk about this now. Do you have it?
This way.
Not exactly. How do you show ionic bonds? Do you show a line connecting the
No.
ions? No. So there should be no line connecting the sodium ions to the carbonate ion. All you have to do is you draw them next to each other because we know positive is attracted to negative. Now, what should I do? Should I put the two sodiums on top of each other?
No.
No, because are sodiums attracted to sodiums?
No.
No. The sodiums want to get as far apart from each other as possible. The sodiums want to surround themselves with negative. And so if you put the two sodiums together like this is not good. This is going to generate big repulsion here. You need to insert a carbonate between them to keep things under control. If you did this where you just say, oh, two sodiums, then where are you putting those? Are you putting them superimposed on each other? That's what it looks like. That's not right. You want to put the sodiums far apart from each other, but next to the carbonate. And so you'd expect the sodiums to be on opposite ends, and then the carbonate here. But this is not the lattice. This is what we call a formula unit. So this is one formula unit. The actual lattice is going to be a three-dimensional network of the ions just trying to maximize their contact with the opposite charged species. And so if we got a sodium here, that's positive. What is the shape of this? Do you guys recognize this shape?
No.
Not tetrahedral. Trigonal planar. Trigonal planar is just a flat pancake style shape. This is negative. And so when we build up the lattice, we want to put as many of these pancake things as we can. Maybe we can't get 4 or 6 of them. Whatever we can get in there. In chapter 12, we'll talk about lattice structures. But we build up lattices like this. Do you see? Etc. And so this would be kind of the lattice for this. Now, having big bulky ions like this versus small compact, like for example, versus sodium oxide, what do you expect to be a stronger lattice? Which one do you expect to have stronger ionic bonds? Yeah, to the smaller one. You don't have this big ion that's triangular shaped and that's got this negative charge spread out around it. You'd expect this small spherical, these are 2 minus by the way, sorry. You expect this small spherical oxide. Oxide, what does it look like? It looks like this. It's just a round ball with a 2 negative charge, and it's quite small compared to a carbonate, and so you'd expect the sodium oxide lattice to be quite a bit stronger. Well, what does that mean? It means it's harder to melt. Melting, you have to break apart all the ions in order to melt it. Maybe it's harder to dissolve in water. Even though both of these should be soluble. And so, etc. Well, what are we doing here? What we're trying to do is we're trying to get as much information about these compounds and elements, we'll talk about the elements later, about these species here as we can on pencil and paper. And so normally when we're trying to analyze compounds or elements, what do? We use the theory of chemistry. And so let's take a step back and look at extracting information about compounds and elements. And so when we're looking at compounds and elements like this, what's the theory? Why do these things bond? Why do compounds form? Well, compounds form is because these bonds make things more stable. Otherwise, it wouldn't form. And so we're looking at the bonding. Well, what dictates the bonding? Well, you know how the electrons are distributed, right? And that kind of stuff. And so when we're thinking about compounds and elements, we think about quantum mechanics. And the what's the equation? The Schrödinger equation, right? Quantum mechanics and the Schrödinger equation. And from quantum mechanics and the Schrödinger equation, we can get things like the structure. We should be able to predict the structure. When we think about the structure consists of two things. If you want to know the structure of something, you need to know the bond distances. That is how far apart the atoms are, and the bond angles. If you have the bond distances and the bond angles, then you know the three-dimensional structure, or the three-dimensional arrangement of the atoms, ions, or whatever is making up that species. But what else do we want to know? We want to know structure, and we want to know
Shape?
the shape. The shape is this. This is the shape.
The size.
Polarity.
Yeah, we want to know the polarity. What else do we want to know? So structure, well, from the structure we could get polarity. Intermolecular forces we get from polarity in the structure. And so, all those stuffs come intermolecular forces. We also want to know things like the spectra. That is, how this interacts with light. And so we have the visible, for example, red food color. We'd like to be able to predict that red food color is going to absorb in the green and the pure red. And so how do we predict that? Well, got to think. We want to know about the UV spectrum. We want to know about the spectrum is singular, spectra is plural. So visible spectrum, UV spectrum, infrared. Infrared deals with vibrations. Right? UV and visible deal with, well, UV is bond breaking, but visible is maybe electron excitement. Yeah, UV is electron excitement, but a little bit too excited. And so we're looking at, if we're looking at electrons, we need to know the orbitals, right? In other words, electron cloud. What are the allowed energies for the electron? What are the forbidden energies for the electron? The microwave spectrum. All these are going to be related to how that electron cloud is distributed in the compound, in the molecule. Okay, what else do we want to know? We want to know about reactivity, chemical reactivity, etc. And so typically we could use quantum, and the Schrödinger equation to try to predict these things, right? Predict. But using quantum mechanics to predict this type of stuff, in order to do it quantitatively or semi-quantitatively, we need to do some calculations. And to do those calculations, we use some computer programs like Spartan. Spartan is a program we have here, but the problem with Spartan is it's very expensive. One time a student asked me how much is it because they wanted to buy it. And so I went up and looked at the academic price. The academic price was like $2,500, so he passed. This is a true story. He wanted to get it for himself. He was thinking it was more like going to be like $30 or $100 or something. But that's academic. Academic is deeply discounted. The normal regular retail price of Spartan is, I think, over $10,000. I think it was like $15,000 or something like that. That's for one computer. Are you gonna buy that? No. This is like having a fancy calculator. You know, I don't have to really think about it. I got Spartan. I can just go ahead and calculate things, right? But you aren't always going to have that fancy calculator. You know, sometimes you'll have to know how to do things by hand. And so, you know, how much of a disadvantage are we by doing things by hand? You know, what kind of information are we not going to be able to get, or can we get all the information? It turns out we aren't going to be able to get all the information, but we can get quite a bit of information by doing it by hand. So chapters 10 and 11, we're going to see what the maximum amount of information we can get is from analyzing these things. And so let's take a look at the first part of this section, and that is, let's take a look at ionic. We have ionic versus polar covalent versus covalent bond. And so first we're going to just look at the individual bond, and then we'll look at the full structure. Looking at the individual bond, let's say something like sodium. Sodium, does it have a very high ionization energy? No. And so therefore chlorine can come and easily ionize it. Boom. Take that electron and we form sodium chloride. Sodium chloride looks like this as far as the formula unit goes and Lewis structure. But when we look at the electron density, the electron cloud, you know, sodium is like this. Then we got chlorine. How should I draw it? Actually, let's draw it in here. In other words, chlorine pretty much has all the electron density here. And chlorine's been stripped of electron density. It only has the core electrons left. And so one way of thinking about this is we got a positive here species and a negative species here. And that's it. And so this would be ionic. All right, then we go to something like polar covalent. Polar covalent would be something like hydrogen and chlorine. And so these would be the Lewis symbols, or Lewis dot symbols for hydrogen and chlorine. But the difference is sodium has an ionization energy of 500 kilojoules per mole, but hydrogen's ionization energy is more like 2,000 kilojoules per mole. And so 500 versus 2,000, that means hydrogen is going to be a lot harder to ionize. Much, much harder. I think it's over 2,000. I think it was maybe 2,500. So when a bond forms here, chlorine just doesn't have enough of an electron affinity to pull that electron off. And so what ends up happening is there's a bit of tug of war going on here. And hydrogen doesn't completely let go of that electron. And so we have some sharing going on here. When I say sharing, it's not even sharing, because it turns out that hydrogen has a weaker pull for the electron than chlorine. In other words, looking at the electron affinities, chlorine has a greater pull. But, you know, using numbers like 2,000, 2,500 versus 500 kilojoules, that's fine, but it's inconvenient. And so we need a simpler way of gauging, you know, this, and the simpler way of gauging this is this. Sodium has what we call an electronegativity of 0.7. Electronegativity. And how would you define electronegativity? Electronegativity is the ability to attract an electron. And so 0.7 versus chlorine. Chlorine's electronegativity is 3.0. And so who has a stronger ability to attract an electron? Chlorine. Much stronger. And so if there's a tug of war for the electron, sodium is going to lose. It's too weak to hold on to that electron. Whereas hydrogen has an electronegativity of 2.1 versus 3.0. This is a much closer match. But still, chlorine is a little stronger. Since chlorine is a little stronger, it's going to pull more of the electron cloud towards it. And we create what we call a bond dipole. There's two ways of showing a bond dipole. Here's the positive end, here's the negative end, here's the positive end, here's the negative end. In other words, we create a polar covalent bond, polar being a dipole like that. Versus in a covalent bond, let's take chlorine, two chlorines. If we take two chlorines, then each chlorine's a 3O, so if there's a tug of war, who wins? No one, and it ends up being a tie. And so we show that like this. And so covalent bonds, whether they're polar or nonpolar, this is called a nonpolar. The reason it's called nonpolar is because the electron cloud is symmetric here. It's not polarized to one side or the other. And so it's even distribution. And so this is nonpolar. Covalent. And so what we see here is just this. This is the most polar ionic bond. This is a medium polarity, a polar covalent, and this is the least polar, which is a standard covalent bond or non-polar covalent bond. So we have that. What holds the bond together here? What holds the ions together? Just electrical attraction, positive being attracted to a negative. Right? What holds the atoms together here? They share electrons? Okay, sharing electrons. When I think about physics, you know, is there a force called sharing? You know, I know gravitational. There's a gravitational pull, right? I know electrical pull. There's electrical pull. I know nuclear forces, nuclear binding energy. But is there something called the sharing force? You know, sharing. Nature wants to share, be at peace. That would be great, wouldn't it? That would be great. And so this has the greatest sharing force. The sharing force holds things together. You know, they shake hands. And they're at peace. Is that right? The sharing force is it? So I mean, so what? They share electrons. Why does that hold the atoms together? How does sharing hold the electrons together? Because when I think about electrons, they're negatively charged. Electrons want to repel each other. Do you want to put too many electrons in one basket? No, you can't, because one, electron-electron repulsion, and two, Pauli exclusion principle. You can't put too many electrons in one basket. And so how does sharing, I mean, if I think about this, doesn't sound right because the electrons are, you know, going to repel each other, so they're protons, right? And so it's not, you know, what it is this. If you added something, you know, they share electrons, which concentrates the electron density in the internuclear region, and the protons in the nucleus are attracted to electrons. Since electrons are concentrated here, the protons are going to be pulled towards the electron density. And that pull towards the electron density is going to hold the atoms together. And so what holds these together? Electrical attraction. That's what holds the covalent bond together here. what holds this covalent bond together? The same thing. There's electrical attraction to this electron density here in the bond, what we call the bonding region. And so these are going to be cold. That plus the charge. You know, this is called a partial positive charge, a partial negative charge. So there's going to be ionic. In fact, there's going to be both. There's going to be an ionic, which is the attraction of the charge, plus covalent, which is this concentration of electron density in the internuclear region, which causes the nuclei to be held together. And so what holds all bonds together? The same thing, electrical forces. Electrical forces hold all bonds together. In fact, chemistry is all electrical forces. This is positive being attracted to negative. This is why quantum is so important, because we've got to see how the electron cloud is distributed to see how the forces are. All right, so this is the bond, and so the first step is we're just going to try to figure out the structure of these things by generating Lewis structures. This is the Lewis structure for sodium chloride. This is the Lewis structure for HCl. This is the Lewis structure for Cl2. And so we look at these. And so Lewis structure, we just did Lewis structure for ionic compound. Lewis structure for ionic, we did two examples, sodium chloride and sodium carbonate. Okay, next we're going to look at Lewis structures for covalent species, or covalent bonds. So Lewis structures for ionic bonding. Okay, now let's look at Lewis structures for covalent bonding species. Okay, there are multiple subcategories to this. And so the first subcategory are the polyatomic ions. Polyatomic ions, like the one we just saw, these are covalent bonds holding the carbon and oxygens. And so there's both covalent bonding and ionic bonding, because the ionic bonding holds the ions together. The covalent bonding is what's holding these atoms together. Is this a non-polar covalent bond, or is this a polar covalent bond? It's a polar, because what we do is we look at the electronegativities. Oxygen is a 3,5, carbon is a 2,1, and there's a significant electronegativity difference, which means that the electron density is pulled towards oxygen. 3,5 versus 2,1. Again, 3,5 versus 2,1. 3,5 versus 2,1. And so each of these bonds is what we call a polar covalent bond. But you look at how these polar covalent bonds are distributed in three-dimensional shape. Space. In 3D space, if you look at how the electron clouds are distributed, is it more isotropic, i.e., is it more symmetric, like spherical symmetry, or is it more anisotropic?
Could you define?
Could I define isotropic versus anisotropic? No. Does somebody have the definition? Isotropic means kind of the same distribution. Anisotropic means a lopsided or clearly asymmetric distribution. And so would you say this is more an isotropic, symmetric distribution, or an anisotropic? This is more isotropic. And so what tends to happen is, even though the bonds might be polar, the molecule could be non-polar, even with polar bonds, because it's isotropic. Right? It evens out or cancels each other out in three-dimensional space. However, this is not, when we talk about polar molecules, we're talking about dipoles. Dipoles have a positive end and a negative end. This is tricky because this is what we call a monopole. What's a monopole? Just one charge. This is polar, yes, because it's a monopole. But it's not dipolar in that there's a positive. Well, it's not dipolar in that there's a net positive and a net negative end, in a sense. I'll come back to this. This one's quite tricky. Well, anyway, we have polyatomic ions with covalent bonds. What else do we have with covalent bonds? We have molecules. Molecules like chlorine, which has this is what we call the non-polar covalent bond, molecules, or polar covalent bond like HCl. Right? Is that it? No. What else do we have with covalent bonds? We have one more. We should be aware. This is called the network covalent. Structure. Network covalent would be like diamond. Diamond forms a lattice of carbon atoms. Have you seen these wedges and dashes? What shape is this?
Tetrahedral.
Tetrahedral. And what diamond is it's just a three-dimensional tetrahedral network of carbon atoms that just keeps going. And so we set up not an ionic lattice, but this is called a covalent lattice. So if I had a mole of diamond, am I just breaking one mole of carbon? No, I'm breaking a whole lattice full of it, which is quite a bit of energy. And so diamond would be an example of a network covalent species.
So would that be symmetric? Or isotopic?
Yeah, this is non-polar. This is isotropic in that sense. It's non-polar. Diamond's non-polar.
What kind of lattice did you say that was? Network lattice?
Network covalent lattice versus the ionic lattice. Lattices are quite strong because it's built up of many bonds. Does it?
Polyatomic ions, do we have to put them in the brackets every time when we draw?
Yes. For Lewis, if it's a Lewis structure, you always have to use the square brackets. For
Even if it's not an ionic bond?
Yes. So for Lewis structures, you need the dots, and you need the bracket, and you need the net charge. If we're just doing regular, that's chloride. But if it's a Lewis structure, this is it. The Lewis structure here. This is the Lewis structure. Equals this, but it does not equal that. So if I ask you for a Lewis structure and you drew this, then yeah, right. I'm going to deduct points. Well, let's do some Lewis structures now. You guys remember the rules for Lewis structures? Step 1.
Carbon in the middle.
Carbon in the middle.
Not everything has carbon.
Well, that was the first time.
Carbon in the middle. Carbon in the middle works sometimes, most of the time, unless it's an easier. Sum total of electrons.
Oh, yeah.
Step 2. Sum total of valence electrons. Step 2 is you build a skeleton structure. The skeleton structure could have carbon in the middle. It might have oxygen in the middle. Oxygen likes to be a good bridge, like an H2O, But normally in the middle, you put the least electronegative element in the middle. The reason is so that the more electronegative elements can attack it, and take away electron density from it. And then you do what? You complete the octets to the outer atoms. If you have leftover electrons, you place those on the center atom. If you run out short, if you come out short, that is, not everything has an octet, then you make double bonds, or triple bonds, or multiple bonds. And so let's start off with draw the Lewis structure for this HCO3 minus. So why don't you go ahead and get started? So the first step, a lot of people skip the first step because they say, I don't need to total up the electrons. But one of the biggest mistakes that I see is that people have way too many electrons. You know, they put in 2 extra, 4 extra electrons in the structure. It's wrong. They didn't realize there were going to be double bonds in there.
Can you list the steps again in order?
Well, we're going to do them. Step 1. Total up the
Valence electron.
valence electrons. So do it now. It should
23.
take 2 minutes at the most.
I forgot, when you have the minus, you add that as a valence electron.
Right.
You have to have an even number.
You don't have to have an even number, but you would add it. -1 just means 1 extra.
Okay.
Can you tell me when somebody has it? 24 electrons, good. How did you get it? Well, hydrogen has how many valence electrons? 1. Carbon?
4, sorry.
Oxygen, we have 3 oxygens. 6, 18.
Plus 1.
And then the -1 charge means 1 electron. And so that gives us 24 electrons. All right, let's go to the next step. Build a skeleton structure. You know, you want to connect all the atoms with bonds. This is a covalent. A covalent ion, it's a polyatomic ion, or covalent compound is going to have lines connecting the species. An ionic compound, a metal and a nonmetal, there are no lines connecting the species. So, you know, one of the hints that, and this is not always 100% true, but usually you put the least electronegative atom in the middle, which would be carbon. Actually, hydrogen. Hydrogen's the least, but you know, can hydrogen be in the middle?
Nope.
No. Okay,
Should be on the outside.
so come up with a skeleton.
The most the least.
That's
So
it.
you're good at this?
That's in minus and 24.
Wait, why didn't you say you were good at this?
Not exactly.
Actually, if you're going to do that,
All right, the first thing, okay, I looked around and saw some things. Hint number 1, is this an ionic compound?
No, it is
No.
not.
This is a covalently bonded polyatomic anion. And so, in order to be an ionic compound, we'd have to have like a sodium bicarbonate. Now, sodium bicarbonate, you're going to have a sodium ion here being attached to the bicarbonate ion here with a ionic bond. But the hydrogen, is the hydrogen ionically bonded to this? No, no. In fact, this is what we call an acid anion. And let me give you hint number 2. Hint number 2. For acids, the acidic hydrogen bonds to the
oxygen.
most electronegative element. It's not always oxygen, but the most electronegative element. And so this hydrogen, even though it looks like it's bonded to carbon, isn't. This hydrogen should be bonded to oxygen.
But which one?
Doesn't matter.
Yes, it matters. Which oxygen?
What did
To which oxygen? We'll figure it out.
what did you say that it's when is H bonded to the most electronegative?
When it's an acid. This is an acid.
Yeah, I know how to do that.
And so the acid, H, is bonded
We can do it like this.
to the most electronegative, I'll call it En, atom. And so this H is, even though it looks like it's bonded to the carbon, it isn't. This H is actually bonded to the oxygen. Which one? You'll have to figure it out because of the three of them. Let me give you some more examples. HClO. What's the name of this acid? HClO. Hypochlorous acid. Hypochlorous acid, is the hydrogen bonded to chlorine or is the hydrogen bonded to?
Chlorine.
It's bonded to oxygen. Why? Oxygen is more
Electronegative.
electronegative, etc. What's the name of this acid? HClO4.
Chloric.
Perchloric acid. Is the H bonded to Cl or is the H bonded to oxygen?
Oxygen.
The H is bonded to oxygen. It looks like this. What's the name of this acid?
Acetic acid.
Acetic acid. This H is bonded to this carbon?
Nope.
No, this H is bonded to
Oxygen.
the oxygen. What about these three H's? Are these three H's acidic?
Can't have two hydrogens.
No.
No, these are not bonded to oxygen. These must be bonded to carbon. So acidic hydrogens are always bonded to the most electronegative element. Why is okay? Let's go here. Fluorine is a 4O. Oxygen is a 3,5. Nitrogen is a 3O, I think. It turns out that chlorine is big, right? Since it's big, it's not going to have the same pull for an electron way out there because it's pulling from a farther distance, number one. Number two, chlorine's actually a 3O. And so chlorine and nitrogen should be tied. Do you know that? But if you guys remember hydrogen bonding from intro chem, hydrogen bonding only occurs when hydrogen is bonded to one of the three most electronegative elements on the periodic table. The three most electronegative elements are
Oxygen, chlorine.
fluorine, oxygen, and nitrogen. But nitrogen and chlorine are 3O. Why isn't it the foremost electronegative? Because chlorine and nitrogen are both 3O. And the reason has to do with size. Nitrogen is a heck of a lot smaller than a big chlorine, and therefore nitrogen is going to have that stronger pull overall. Well, anyway, let's go back to this here. It's going to be oxygen. One, oxygen is a heck of a lot smaller, and two, its number is actually bigger.
Do we have to remember the electronegativities for this test? 3O.
No, you don't have to remember the numbers. You just have to remember the trend. The trend is the smaller the atom, the higher the electronegativity. Except for helium. Helium is the smallest, but the electronegativity is fairly low because helium does not want another electron. So fluorine ends up being the highest. All right, so why don't you redo your structure, your skeleton structure, and see what you come up with.
Here it goes. So now what's this?
Okay, that's good. That's good. All right, so the skeleton structure, we put carbon in the center and then have the oxygens attacking it. You know, the oxygens are trying to take electron density, usually. And then we pick one of the oxygens for the hydrogen. Which one do we pick? Does it matter?
No.
No, they're all the same, so just pick one. We'll pick the top one
What
here.
about the common bonding pattern?
The common bonding pattern?
The what?
What's that?
I don't know. Jimenez was saying something like, oh, you can put it there, but because of the common bonding pattern, you have to decide. Something. It was last semester. I forgot.
Okay.
Maybe it's not.
Well, it was probably different names for me,
Oh, okay.
but everybody has their own name for things. So how many electrons have we used up? 2, 4, 6, 8. 8 of the 24. We have 16 electrons left. So the thing we got to do is we complete the octets to the outer atoms first. The outer are more electronegative. The more electronegative species are going to take the electrons first. And so we complete it there. We complete it here. And so that takes care of 20 electrons. And so we have 4 left over. And so we'll complete this oxygen here. And then, do you guys remember how to count octets?
Yep.
Yeah. And so hydrogen doesn't get an octet. Hydrogen gets a duet. But the first shell only takes 2 electrons to fill. And so we filled the first shell here. Oxygen, we double count, right? And so we look at the total number of electrons surrounding, 2, 4, 6, 8. So oxygen has an octet. How about carbon? Carbon does not. Carbon has 2, 4, 6. These 2 oxygens, yes. 2, 4, 6, 8, 2, 4, 6, 8. And so since carbon hasn't filled that shell, what do we do here? We take an electron. And so we have 3 choices. This is choice 1. We'll take an electron from here, bring it there. If we follow choice 1, we get this structure here. And when we do that, we just completed carbon's octet. Did we sacrifice oxygen's octet to make carbon's octet? No. Because this oxygen still has a octet. And so we're good. Let's choice 1. We have choice 1. We have choice 2. We didn't have to take this oxygen. We could have picked any of them. So let's pick this oxygen. We'll take this pair of electrons and then just donate it to the bond. And so that would be choice 2. Let's write that over here. So we generate this structure instead, where we create a double bond here. That's choice 2. And again, we gave carbon an octet without sacrificing the oxygen octet. So that's good. But we also had choice 3. Okay. So this would be 2 instead of 3. If we do 3, then what we're going to have is we're going to have the double bond down here. And we're good. And so this is the way we can generate the octets around everything. You know what these are called? These are called resonance forms. Except 2 of these look the same, the third doesn't. Which one looks a little odd? The first one. The first one looks odd because why? Well, it just looks different. But is it okay, the first one? Why is it not okay?
Oh, this is a common large pattern. That's what he was talking about.
There's a rule, I forget, but I know it has to be.
What is the rule?
You count the bonds, the single bonds, as one, and you have to count the electrons.
I've seen oxygen with 3 bonds. You know the hydronium ion? Hydronium ion has oxygen with 3 bonds. So what is the rule? Hmm? The first one looks funny. What's wrong with it?
It's the charges. But the first one is going to have this polarity somehow.
Well, they're all going to be polar to some degree because of the oxygen-hydrogen link.
The first one doesn't happen as easily.
The first one, what?
It doesn't happen as easily.
It doesn't happen as easily. And what is the reason why it wouldn't happen as easily?
Stable.
The first one's less stable. Why is it less stable? Because everything has an octet. Everything's happy.
You minimize the charges on each.
Yeah, the charges are not right.
The charges are not right? Well, let's look at the charges here. What are the charges? All right. This is, we have to talk about this because when we're talking about charges, we talked about oxidation states, right? We have to talk about another type of charge. There's another type of charge, it's called formal charge.
Yeah, that's what I meant.
Okay, the formal charge is this. In formal charges, we assume something. You know, when we're doing oxidation state, what do we assume? Like, for example, let's calculate the oxidation state for this oxygen. When you look at the oxidation state for the oxygen, winner takes all. If winner takes all, then oxygen ends up with 2, 4, 6, 8. It's minus 2. Minus 2 sounds totally reasonable. And so for oxidation state, you know, winner takes all means this. Oxidation state, we assume 100% ionic bonding. 100% ionic bonding is winner takes all. These are the more electronegative species. And then we count the charge. Is it accurate 100%? No, but you know, it's normalized so that we can make good comparisons. You know, because we're comparing oranges with oranges. Well, formal charge, we make the opposite assumption. In formal, what is the opposite assumption? We assume 100% covalent bonding. And so in ionic bonding, winner takes all, right? But when you do formal charge, it's sharing, you know, that kind of sharing thing. And so when we're doing the sharing thing, we're going to split all electrons evenly, even if the other atom is weak. And so here, oxygen could easily take most electron density from hydrogen, but it doesn't. It shares, and it shares 50-50. And carbon versus oxygen. Oxygen again is the winner, but oxygen is going to share and split the electrons right down the middle. And so when we do the formal charge, the count is different. When we do the formal charge, hydrogen has a formal charge of, well, it's got 1 electron. It's supposed to have 1 electron, so it broke even. It has a formal charge of 0, but its oxidation state is +1. This oxygen has an oxidation state of -2, but its formal charge is actually 0 because it's got 6 electrons. It's supposed to have,
Wait, 5.
oh, wait a minute. It doesn't have 6. It's supposed to have 6. It only has 5, so it's formal charge is actually plus. Now, with formal charges, we circle them. And so this would be a +1 formal charge. Let's see. Okay, whereas this oxygen, let's take a look at this oxygen. If we split it down the middle, it has 1, 2, 3, 4, 5, 6, 7. It's supposed to have 6, so this has got a negative. The same thing, this is the same, so this is negative. And that means carbon is 0. And so those are the formal charges. Now let's compare it to this structure over here. When we split it down the middle, this oxygen now has 2, 4, 6. This is 0. This oxygen is 0. And this oxygen is minus. This carbon 0, this hydrogen 0. And so now we just have one formal charge over here that's minus. And so the way we think about it, to go from this structure here to this structure here, that means this left oxygen must have taken an electron from this. And so this electron gets switched over here, which means that this one goes up to +1, this one goes down to -1. And so, in other words, if there's a tug of war for an electron, who wins? Which oxygen wins? It's oxygen versus oxygen. If there's a tug of war for an electron, and you have two oxygens, then it should be a tie. And so this is unusual. Would this be a ground state? No, we'd call this an excited state because it can't maintain this for very long. It can't maintain this for very long because the oxygens are going to settle. And so this structure is less stable, higher energy. And so we eliminate this as a possibility because it's not as stable as the second and the third. And the second and the third, if you look at them, they look very similar, right? In fact, they look the same. And so because of the formal charge separation here, this is unstable. And so now we look at these two structures here. Now when you do this, a lot of people will say, hey, you know, these are the same structure. You just flip it, right? If we take this structure and flip it 180, then it's the exact same as that. But you can't do that. For resonance structures like this, what we're generating is you have to pin the atoms to the ground. You have to pin them on the board and then see how you can distribute the electron cloud. You never move the atoms. Never move the atoms. And so it turns out that there are only two possibilities for arranging the electron cloud. Let's talk about those here. The two possibilities for arranging the electron cloud are like this. We can have the double bond on the left, single bond on the right, and then the hydrogen goes up at the top here. And then we show it with a double-headed arrow like this. Or we could have the double bond on the right, single bond on the left, and then the hydrogen going up here. We have these two structures. This has a negative charge here. And what we do is we need the square brackets because what the square brackets show is this. We're going to sum up all the formal charges. When we sum up all the formal charges, we get the net charge. The net charge equals the sum of the formal charges. And so here we now have the formal charge over on the left, and the net charge is still -1 here. What about this? I'm going to move the hydrogen from here, the top one, to here. Is this a third form? No. Never move the atoms. You can only move the electron density, the electron cloud. Never move atoms.
So what would that be called? Is there certain definition?
What would this be called? This would be called going in an infinite loop. Because people who move the atoms, when I ask them to draw the resonance forms, end up drawing 50 different structures or something like that. It's ridiculous because they'll put the hydrogen here and then move the double bond here, and then the next one will have the double bond here, and then they'll move the hydrogen over here, move the double bonds like that, right? And they end up drawing way more structures than they're allowed. Because the whole purpose of resonance forms is this. The whole purpose of resonance forms is to see how the electron cloud can distribute itself in the structure. And when we see two resonance forms like this is how the electron cloud distributes itself. We can see that we could have the double bond over here. When we have a double bond over here and a single bond over here, actually what we could do is we could interconvert. That is, if we take this pair of electrons here and make a double bond here, that means there's too many electrons here, we kick a pair out. And so if we bring a pair in, kick a pair out, we get this structure. Likewise, if we bring a pair in here and kick a pair out, then we revert back to this structure. And so you can see how the electron cloud can rearrange itself to generate these two without moving any atoms. You know, is it okay to bring the electron pair down here? No, because that costs too much energy, so that's not okay. And so the electron cloud doesn't change up here. The electron cloud could move around down here. And so if the electron cloud's moving like this, then what is the origin of the name resonance? Normally when people think about resonance, do you remember the Tacoma Narrow Bridge? You know, the winds hit the resonant frequency of the bridge and it started to sway. Right? And so normally when people think about resonance, they think about cycling, you know, up and down. And so when we think about cycling this, a double bond like this has twice as much electron density. Twice as much electron density is going to pull the nuclei closer together. So double bonds are short, single bonds are long. Double bonds are stronger, single bonds are weaker. And so is it resonating back and forth? Double, single, double, single, double, single. Are the bonds just resonating like this, like an accordion? No. Or look at this, negative, neutral, negative, neutral, negative, neutral. You know, is the charge flipping back and forth like this and resonating? Resonating charge? Boom, 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 boom. Like a ping pong ball? No. No. And so when we think about resonance, it's just showing this, how the electron cloud can be distributed in the structure. We fit these. This is called localized, 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 localized. These electrons can delocalize. And when we think about a cloud, it's like fog. You know, the fog, you can localize the fog in one area, or you can let the fog spread out, right? How do you localize the fog? You build a wall. You build a wall, the electrons can't move. There's a wall here. The wall is called energy, too much energy. These electrons aren't going to move from here to here. The fog or the electron cloud doesn't move, right? But down here, it can move. And so what it turns out being is that neither of these is accurate. You know what the most accurate is? And so these are the two resonance forms. The most accurate is what we call the resonance hybrid. A hybrid, what is a hybrid? A hybrid is a mixture of the two. And since we only have two, it's going to be a 50-50 mixture of the two. And so what the hybrid looks like is this. The hybrid is going to have this fixed, and then it's going to have a single bond fixed. But the double bond electrons are like a fog, or like a cloud. And the double bond electrons just spread out over both bonds. Okay. And there are going to be 2 lone pairs fixed on each oxygen, but the third lone pair spreads out. And so rather than having a double bond and a single bond, do you know what we call this bond? We call this a 1.5 bond. This would be a 1.5 bond. And rather than having a negative on this and a 0 on this, we end up with a -1/2 formal charge on this and a -1/2 formal charge on this one. And so the analogy is like this. The analogy is these electron clouds are like water, and they want to, seek out the lowest energy possible. And so when we're looking at this scenario here, this scenario, if we just look at the bottom part of this, and imagine that we build a bathtub that has this kind of V shape like this, upside down V shape. And we say, is it possible to put 2 feet of water? I want to put 2 feet of water on the left side and leave 1 foot of water on the right side. Is that possible? Sure, it's possible if there's a wall between here. But it turns out there's no wall because you see the electron density can redistribute itself between these two. And so if there's no wall here, well, what we could do is we could push all the water to the other side as well. And so is resonance like this? Is resonance putting 2 feet on the left and then pushing all the water to the right, or a lot of it, to the right to get 2 feet on the right and then 1 foot on the left? And so is resonance this 2 feet of water, 1 foot of water, 2 feet of water, 1 foot of water, resonating back and forth? Yes? No. That's not what resonance is. Resonance is just showing how the water can redistribute in the structure so that we can end up generating the resonance hybrid. And the resonance hybrid is going to show us, well, we see how the water can redistribute here, and so we're going to come up with the resonance hybrid. The resonance hybrid is going to be a tub that's going to be filled with not 1 foot or 2 feet, it's going to be filled with 1.5 feet on each side. Does that make sense? And so, in other words, the electron density is going to spread out and even itself out.
Oh yeah, good. Okay.
If it's possible. This is the resonance hybrid. And so what we're after by drawing all these resonance forms is we want to see how the electron density can distribute itself in the structure so that we can smear it out when we come up with the hybrid. And the hybrid's going to be the most accurate. And so why don't you try this? Why don't you generate all the resonance forms for carbonate, generate all the resonance forms for carbonate, and based on the resonance forms, draw the resonance hybrid. And so do the same thing for carbonate that we just did for bicarbonate.
How do I do the formal charge?
The formal charge is a 50-50 split down the bonds. So just box it. It's not winner to the bond. Yeah, tell me what the non-zero formal charges are.
Oh, non-zero.
Do the formal charge.
I'm doing it right. Yeah, I did it. But you have to draw the hybrid too.
Oh, no, no.
I did it already. You asked what the house should be like.
Do you have to do the brackets around it?
You have to do the brackets around it, showing the net charge, which is the sum of all the formal charges. Yeah.
So the formal charge, you have, say you have a double bond.
Split it down the middle.
So
Yeah.
it's 1 and 1.
No, 2 and 2. 2 electrons go to one atom, 2 electrons go to the other. That's a double bond. In a double bond, you have a total of 4 electrons, and there are 2 lines. Each line represents 2 electrons.
And when one wins an electronegativity, they take them all.
No,
They just take the ones that are.
it's a even sharing thing. Formal charge is like oxidation state is winner takes all. You know, winner takes all. Whoever's more electronegative is the winner. Formal charge, they don't care. You know, formal charge is even if it's a weak atom with a very low electronegativity, it still gets its fair share.
Does the hybrid have brackets?
Hmm?
Yes.
The hybrid has brackets.
The hybrid has brackets too. You got the hybrid. It has to add up. You know, the formal charges have to add up in the hybrid.
So you can check your work.
Yeah, I'm going to check these off.
Huh? I don't know how to do the formal charge.
You don't do it in your lab book. Do it in your notes, notebook.
Stop. She's just weird.
So I guess.
Like that, except tell me what the bonds are. Are the bonds 1.5 bonds or?
I did.
What do you like?
Okay, you only got 2 resonance. Oh.
Do you write on it the two-third bond?
Yeah, something like that.
And you go like, so